Hi, I'm Hongyu. I'm here to present Ocean, online task inference for compositional tasks with context adaptation. This is joint work with Yuke, Jure, Anima, and Animesh. In this work, we aim at meta-reinforcement learning where we have a distribution of tasks. The goal of meta-RL is to train an agent that can achieve multitask solving ability, and given a new task during test time, the agent can quickly adapt to it without the need to train from scratch. In this work, we build upon a class of meta-RL models called context-based meta-RL, where the idea is to explicitly perform task inference using contexts and disentangle task inference from decision-making. The contexts are simply a list of transition tuples of a given task, including the state, action, reward, and next state in a certain time step. And we assume that if two tasks are different, they may also have different contexts. So we can use context as a nice representation of the task and can distinguish tasks using the context. As shown in the slide, the agent is task-aware in decision-making since it takes a state S and also a latent context variable Z as input and outputs the action A. Based on this setup, we also find that real-world tasks are often complex and compositional, meaning that they often require finishing a sequence of subtasks. For example, opening a door requires an agent to reach the doorknob, rotate it, and push. In order to train meta-RL agents, inferring the task accurately is important, especially in real-world scenarios where there are many subtasks, and the subtasks may change randomly or are conditioned on how or whether the previous subtask is finished. As an example, the agent currently has 3 potential goal locations, and one task requires the agent to go to each of the 3 goals in a specific order. Then the agent has to figure out the 3 goal locations, which represent the global task structure, as well as know what is the current goal, which may affect the agent's policy in each step. Inspired by this observation, we aim to design a task inference framework that covers both the global task structure as well as the local current subtask. Since the subtask is changing, it is crucial for the agent to infer the subtask in an online fashion and keep updating its belief over the subtask. In this work, we propose Ocean, an online context adaptation framework for accurate task inference in meta-reinforcement learning. We introduced 2 modules for inferring the global task structure as well as the local task structure. As for modeling the global task structure, we use the past context of the task and represent the global task with a mixture. For example, the task on the left requires the agent to go to red, green, and blue locations, and the task on the right requires the agent to go to brown, red, and blue locations. And inspired by the topic modeling, we use a structured global latent space, specifically Dirichlet distribution, to model such proportional data. Besides, our model also supports a flexible parameterization of the latent space, so that the users can choose the appropriate latent distribution based on the prior knowledge of the general task structure. As for local task inference, we update the local context variable online using a recurrent neural network. Specifically, we accumulate the past context within the episode, which represent our understanding of the history information in this episode. And we use this past context to infer the current subtask. These past contexts contain rich information regarding the subtask. For example, if the current goal location is blue, then one action towards the blue node will give us a high reward. However, if the current goal location is red, then the same action towards the blue node will give us a penalty. And all of this information is stored in the transition tuples. Since local task inference is essentially sequential, so that it may require additional computation cost to update the local context variables. However, we can amortize the cost by only performing local task inference every t steps, since we do not have a new and different subtask for each single time step. It is very likely that the goal position in time step t is also the goal location in time step t+1. Based on the global and local task inference module, Ocean designs a composite latent space and combines global and local context variables together, and the agent uses both in decision making. The local context variables are updated online, while we keep the global context variables the same in an episode. Since our model belongs to the context-based meta-RL, we can train the agent using off-policy update algorithms, such as soft actor critic, which achieves high sample efficiency compared with on-policy algorithms. Note that our model does not require any information about the number of subtasks or the label of the transition steps. Our model can learn the transition in a completely unsupervised manner. We also provide a flexible parameterization of the latent space, including Gaussian distribution, categorical distribution, Dirichlet distribution, logistic normal distribution, and users can choose the appropriate distribution based on the prior knowledge. And for the global latent space, we follow Pearl and view each past context as an independent factor. We performed experiments on Mojoko environments, where we created several new environments with a half-cheetah agent and a humanoid agent. Each new set of meta-RL tasks consists of subtasks and requires the agent to finish multi-stage sub-goals in order to finish the task. Specifically, we design multi-direction, multi-goal, and multi-velocity. For example, in multi-direction, the agent has multiple goal directions to finish the task. We compare our model Ocean with state-of-the-art meta-RL models, including ProMP, eMemo, RL2, and Pearl. Ours are most similar to RL2 and Pearl, where RL2 uses a recurrent architecture for policy network. However, they do not explicitly perform task inference, and they also do not reason over the uncertainty of the tasks. Pearl also belongs to context-based meta-RL models. It only uses a Gaussian random variable to represent the task and uses the same task variable across one episode. So Pearl can be viewed as a special case of Ocean, where no local update is performed. Thus, it's hard for Pearl to model real-world tasks that require finishing a sequence of subtasks. As shown on the slide, our model achieves high sample efficiency and also better performance than previous state-of-the-art models. As a demonstration, we visualize a learned policy of Ocean and Pearl on multi-goal tasks. These tasks consist of 3 goals, and as shown on the slide, our model is able to quickly adapt to each subtask, while the baseline cannot, since it does not perform online task inference. In this work, we introduce Ocean, which performs online task inference for meta-reinforcement learning. Ocean is able to greatly improve the performance and sample efficiency in multiple meta-RL tasks that have sequential subtasks. Thank you.